Water molecules are composed of two hydrogen bonds linked by a single polar covalent bond to an oxygen atom. Water is a polar molecule, meaning the molecule has an uneven distribution of electron density. Water molecules have a partial negative charge near the oxygen atom due to the unshared pair of electrons and a partial positive charge near the hydrogen atoms. Hydrogen bonds are weak interactions which form between a hydrogen with a partial positive charge and a more electronegative atom such as oxygen. Water molecules are bonded together by hydrogen bonding. When investigating water's behavior, it is important to consider water's physical properties. At 100 degrees Celsius, the water reaches its boiling point. This is when the water will gain enough energy to be transformed into vapor, its gaseous phase. Below 0 degrees Celsius, the water loses enough energy to enter its solid phase. And above 0 degrees Celsius and between 0 and 100 degrees, the water will be in its liquid phase. These are termed the freezing and melting points, respectively. A solution is formed when a solute is dissolved into a solvent. Because of water's polarity, it plays a major role in the dissolution of ionic compounds during the formation of aqueous solutions. This has earned it the nickname of the universal solvent. The behavior of water can be linked largely to three major processes. Cohesion refers to the attraction of molecules to other molecules of the same kind, and water molecules have strong cohesive forces thanks to their ability to form hydrogen bonds with one another. Similarly, adhesion is the attraction of molecules of one kind to molecules of a different kind, and it can be quite strong for water, especially when the molecules encounter surfaces with strong positive or negative charges. For instance, when a thin glass tube or capillary tube is placed in a beaker of water, the water in the tube will begin to climb above the water level in the beaker. This is because the attraction between water molecules and the glass walls of the tube, as we now know as adhesion, as well as on interactions between water molecules or cohesion, results in the upward movement of water against gravity. This is known as capillary action. Cohesive forces are also responsible for surface tension, or the tendency of a liquid surface to resist rupture when placed under tension or stress. Surface tension results in the formation of a meniscus at the water surface. The behavior of water in the soil is a result of the forces which act on the water molecules. Soil water flow direction is driven by the water's potential energy, or the work water can do moving from its current state to its reference state. Total water potential is the sum of three forces: gravitational potential, osmotic potential, and pressure potential. Gravitational potential is the force of gravity acting on the water molecules to pull water downward. It can be expressed as the height of water above the reference point. Osmotic potential is the force most responsible for uptake of water by plant roots. Through osmotic potential, water moves from areas of low solute concentration to areas of higher solute concentration, or from less negative potential to more negative potential across a membrane. Pressure potential, which is normally zero in the soil but very important in plant cells, is the pressure imposed on soil water. When the pressure potential is negative, this is matrix potential, or the force of attraction of water to the soil matrix. This negative potential, combined with water's adhesive and cohesive properties, can result in flow of water upward through the soil pore network, much like it behaves in the capillary tube placed in a beaker of water. This flow is termed capillarity, and it differs based on the size of the soil pores, among other properties. Water may enter and exit the soil through a variety of processes. Aside from the upward flow from capillarity, water may enter the soil from the surface primarily through precipitation like rainfall or through irrigation. The process of water entering the soil surface by downward flow is infiltration. Infiltration rate is maximized when the soil is dry but gradually declines as the water content moves toward the saturated coefficient of that soil. Once the soil is saturated or nearly saturated, water then moves downward through the soil due to the force of gravity. This process is known as percolation. When percolating water carries solutes from the soil with it, that process is known as leaching. While leaching is desirable for the removal of excess salts from the root zone, essential nutrients may also be carried to lower depths in the profile out of the range of plant roots and microbes. Water may also be evaporated from the soil surface, counteracting the force of gravity. On bare soil, the radiation balance is a sum of all incoming minus all outgoing radiation. Simply put, energy is exchanged between incoming radiation energy from the sun and atmosphere and outgoing radiation from the soil. Energy which reaches the soil can either be reflected or absorbed. The fraction of radiation which is reflected can be represented by the reflectivity coefficient albedo. The net radiation on the soil surface is transformed into heat, warming the soil and air and causing the soil water to vaporize. Another way in which water exits the soil is through uptake by biologicals like plants and microorganisms. The relationship between the soil, plant, and atmosphere is also known as the Soil-Plant-Atmosphere Continuum, or SPAC for short. SPAC is an integrative system which partially governs water movement. Throughout the system, water moves from regions of higher potential energy to regions of lower potential energy. Once water exits the plant through a variety of processes, it is then recycled into the soil system to begin these processes all over again.